Welcome back, welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel for anything I want to talk about science and math. And today we're doing solutions. Yay! So I got some more subscribers. I'm pretty excited. I'm up to like 570 now. So that's the, yay, I got some subscribers dance. We're still going for 1,000. And you have to prove my children wrong. My 3 sons say, Mom, it's not going to happen, but I can dream. I've had over 30,000 views, so, you know, that's something, because people need to subscribe. Or maybe it's just like 4 people watching them over and over again. All right, so what we're doing today is we are talking about solutions. And this, I think, is the easiest chapter we've done yet, because it's not very math heavy. It's much more vocabulary. And vocabulary, a lot of the vocabulary, you already know. A lot of this is common sense. So I'm thinking this one's going to be good grades for a lot of you. And the last one on pH. You already know about acids and bases. You learned a lot about that in physical science. So I think it's going to be pretty easy. All right. But it's real picky things. Jace, if you keep talking, you're going to be moving back a seat, okay? Put away your phone. You didn't make 100 on your test. Don't talk. Yes, you were talking. Be truthful. Be truthful. All right. Next, what is a solution? Now, in chemistry, we will often use the word solution when it's not exactly technically correct. A lot of times, we'll use the word solution for anything that's in a beaker. If it's in a beaker, it's a solution. But it actually has a technical definition, and it's this. A solution is a mixture that has the same composition, color, density, and taste throughout. It is clear but not colorless. So our example is Kool-Aid. So Kool-Aid tastes the same at the top, middle, and bottom. It looks the same at the top, middle, and bottom. It is not colorless. Kool-Aid does not usually look like water. It's usually a color. My favorite's black cherry, which is a dark red color throughout. Okay, does that make sense? Luis, put away your phone. You didn't make 100 on the last test. Only people who made hundreds. Tristan? Kayla, poke Tristan there. Tristan, put away your phone. You didn't make 100. Put it away. Remember, no phones. This is an easy unit. Don't let your phone keep you from making an easy, good grade on this one. Just put it away. Be strong. And if you need me to put it in my drawer with the calculators to keep you from temptation, I can do that. It can hang out in the calculator drawer if it needs to. All right, so the first thing is there are 2 kinds of solution, and y'all already know the root of this. Does homo mean same or different? And does hetero mean same or different? Different. So our solutions are either homogeneous, the same throughout, or heterogeneous, different throughout. So homogeneous, homogeneous is the same throughout. Heterogeneous, get real quiet, has layers. It has different parts to it that are different. So like salad dressing, that has the oil layer and the vinegar layer that you have to shake before you pour on your salad, is heterogeneous. Homogenized milk is homogeneous. The milk is the same at the top and the middle and the bottom. Now, chocolate milk can be heterogeneous. If you add too much chocolate powder, where it makes a sludge layer on a delicious sludge layer on the bottom, a little treat at the end that you eat out with the spoon, that would be heterogeneous, not homogeneous. My husband makes homogeneous chocolate milk. I make heterogeneous chocolate milk. I like it to have a little layer on the bottom of the chocolate. That's better, right? Nesquik, not Hershey's. No, it's got to be, or Ovaltine. Boo. No, it's got to be Nesquik. I don't want my chocolate milk tasting like vitamins. That's gross. All right. Shh. Get real quiet. Okay, so that was all easy, wasn't it? Next part is pretty easy too. Okay, so we have another way to classify solutions besides heterogeneous and homogeneous or homogeneous, and it is how clear is it? So a solution is clear. Oops, it's not writing good. It is clear. There's another thing called a colloid, and it is cloudy, like milk. So the reason why colloids are cloudy, like milk has suspended in it little globules of sugar, protein, and fat. It's a perfect food. It's got everything in it. Suspension. Now a suspension has chunks in it. Like,
that's not like a bad combination.
It does, but it's not. So if I tell you what it is, think about the Italian salad dressing that's creamy looking, that has like little pepper flakes suspended in it, and you don't shake it first. Do you know what I'm talking about? That would be a suspension. Also, bubble tea. Y'all like bubble tea, right? If the bubbles don't all immediately go to the bottom, if they stay up in the drink, it's a suspension. So suspensions aren't gross. Who likes bubble tea? Where's the best place to get it around here? Domino's?
No.
McDonald's has bubble tea. There's one over near NCG, and there's one on the Marietta Square.
Oh, yeah.
I went there yesterday.
So there's a couple of them. So that would be a suspension if the bubbles don't come out. All right. I'm going to write a little bit more before I scroll.
Kenzie is very mad that you're calling it bubble and not boba.
Not what?
Boba.
Boba?
That's the name of it, is boba tea.
Boba tea.
Boba's good.
Boba. All right.
It really is.
It's the same thing.
All right. The next thing, here's some more vocabulary. It's solute versus solvent. Now, what makes this hard is they're almost the same word, but they have different meanings, and on the test, these will be matching questions. So, the solute, the one with a U in it, is what gets dissolved. The solvent with a V is what does the dissolving. Y'all get quiet. And normally, we think of what does the dissolving as water. Water is the most used, the solvent you're most familiar with. So in this big V, I want you to fill it with water. It won't write. Oh, there it goes. There it goes. So take that V and put water in it. So you can remember that solvent is the liquid usually, and solute is usually the solid. Jace, I want you to move back because you're still talking. Go back one. I understand. Kenzie's very nice to talk to, but go back one.
Because I didn't understand how solvent dissolves.
Ask me. Don't ask her. I know more about it than she does. I'm confident in that. All right, so solute gets dissolved. Solvent dissolves it. Solute is the Kool-Aid packet. Water is the solvent. Okay, we're going to talk about this Kool-Aid packet in a second. It's my prop for talking here. Okay, the next word is solvation, and that is the attraction of a solvent with ions of a solute. So the solvent is actually attracted to the solute and pulls it apart. There's another word called disassociation, and that's when the ionic compound just dissolves from each other. They dissolve away from one another. They're no longer attracted so much. So that's in our standard. If you look over here, one of the things we have to learn is we have to know the difference in disassociation, where it just comes apart, and solvation, where the solvent pulls it apart. Everybody see it here on the thing? I didn't underline this one. Let me underline it. See, that's our first. So see, we've just learned our first standard. Yay. Oh no, where'd it go? No. Okay, I'll have to go fix it.
Backwards. I'm turning in my 10-point.
Put it on my desk. On my desk. All right, what a pain. Don't save. Don't save it all gone away. Absolutely don't save it.
It has my name on it.
I'm grabbing the candy.
I'm grabbing the kids. Why do you have an attitude?
You're impatient.
I'm very impatient. Trust me.
All right, it's back. Okay, our next idea. Yep, just put it right there. Our next idea is aqueous solutions. Now, we learned this when we learned about reactions, that if something is dissolved in water, remember how it's got a little AQ in parentheses? So aqueous solutions are dissolved in water. Now, how does this work? It works on the fact that opposites attract. So here I've got sodium chloride salt, and the sodiums are positive and the chlorines are negative. Does that make sense? Remember that water is shaped like Mickey Mouse with a negative head and positive ears. The negative head lines up with the positive sodium, and the positive ears line up with the negative chloride, and the water pulls the salt apart. Does that make sense to you? This is such a classic picture. It's in every chemistry class. All over the world, everybody looks at this and goes, oh, this is how things dissolve. It's kind of nice. Yes?
It looks more like Kermit the Frog, doesn't it?
See, that's what kids say, is that unimpressed Kermit the Frog or Mickey Mouse. But I have such a good picture of Mickey. We got to go with Mickey because that one's really good. I didn't draw it. My son Josh drew it. Okay, now what can dissolve? When I'm talking about like Kool-Aid dissolving in water, that is a solid dissolving in a liquid. So this would be like sweet tea. You put sugar in tea, you got sweet tea. What else can dissolve? What about soda pop? What about Coca-Cola? What's dissolved into that Coca-Cola? Syrup, but we would be very unhappy if this was not there.
Sugar.
No, when you open it up, it goes.
The fizz, the carbonate.
It's the fizz. We want the fizz. So that is a gas dissolved in a liquid. It also has to do with fish. See my cute little fish here? Fish breathe O2 just like us. They breathe oxygen just like us. They do not breathe the oxygen that's in H2O. Do you see that? They do not breathe that O. They breathe O2 that has been dissolved into the liquid, into water. And if that water gets too hot, the oxygen can come out and it can all cause the fish to die. So sometimes there's a fish kill from thermal pollution. The fish suffocate. All right. And then the last thing, this is what the books always say, is that metal can dissolve in metal. Now, how do they do that? You have to melt it. If you melt metal and pour it into other metal, you can get a mix of metal like brass. Brass is a mixture. Brass is not on the periodic table, so it is mixed where you take other elements, metals, and mix them together. We did that with our coins. Those coins weren't really gold, they were brass. And we mixed the copper and the zinc and made brass. Remember that? Okay, I'm going to try to scroll it. Everybody wish me luck. We'll see how this goes. So far, these aren't hard, are they? Ooh, we did it. Yay. Okay, next idea. You can speed up how fast things dissolve. And we, as proud Southerners, know about this because of sweet tea. Okay, you go up north where they don't know about sweet tea, and you order sweet tea, and they will bring you a big glass of unsweet tea full of ice and a little pack of sugar and a spoon and say, here you go. Will that work? If you pour the sugar in the cold sweet tea, you stir it around, and it's just like a snow globe, right? So you have to stir real fast and then try to drink real fast while the sugar is still floating around at the top. Okay, now, how do we in the South get the sugar in the tea? When do you add the sugar? When it's hot. So one thing that helps speed up dissolving a solid into a liquid is heat. Heat. Okay, but you're up north, they brought you the little packet of sugar. What you pour it in, what do you do next? Trying to hope it'll dissolve. You stir it. So another thing that can help is stirring. Now, there's a new product. It's this, Kool-Aid Singles. It's got real sugar in it. It is not saccharin. Will this dissolve in ice water?
Yes.
Yes, it will. Why? Why will this dissolve in that little packet of sugar that the waitress brought you not dissolve? Yes.
Chemicals.
No. Good guess, but no. There's something else about this. Anybody have this? What's different about it? Why can it dissolve? Why does it look different than regular Kool-Aid? It's more powdery. It's particle size. If you can get the particles small enough and they've ground the sugar really, really fine, it'll dissolve better. So the third one is particle size. So here's our drawing. We've got heat, we've got stirring, and we've got particle size. Now, what can dissolve? This is vocabulary. On the test, this will be matching. Make sure you start studying this. So how much can be dissolved at a given temperature is called the solubility. So how much? So we learned this already. Do you remember when I gave you the nag-sag? Did I give that to you or did I just give it to honors? Did I give you the little chart with the pig saying nag-sag? No. Y'all look very confused. Okay. If you take more chemistry in college, you're going to learn about there are rules about what dissolves and what doesn't. And I have a little pig on the list of rules, and the pig is saying nag-sag because it's telling what dissolves. So y'all don't have to know these rules. Another thing that makes you glad you took regular, not honors. But these are called the solubility rules. You just need to know they're out there. There's rules that determine what can dissolve and what can't. Another word that you're already familiar with is concentration. Concentration. Now, this is not thinking hard. This is, you know how you can buy a Dawn dish soap in a little bottle this big and it's $1. And then there's another bottle sitting right next to it, the same exact size, and it's $3. Why would anybody buy the $3 one and not the $1 one? Because the $3 one says it's concentrated. The $1 one is supposed to have more water, and the $3 one is supposed to have more soap. You're used to that, aren't you? Hearing about things being concentrated. So it's just that. It's how much is dissolved. And we learned about this last unit, Unit 7 actually. The symbol for concentration is the square brackets. So like you could have like, it's like 2M tells you how concentrated it is. Caravaggio, put that phone away.
I got you.
Put it away. Okay, now, no more can dissolve at a temperature. It's called saturated. And you're used to that word too. You're trying to wipe up a spill with a towel and no more, your towel won't take any more. You say that it's saturated, don't you? This towel won't work, it's saturated. Well, this is the same thing with dissolving. If no more will dissolve at this temperature, it's saturated. Some of y'all experienced this with sugar cereal. You had the corn flakes, and you decided to put some sugar on it. And you put so much sugar on it that sugar will not dissolve in the cold milk, and at the bottom of the bowl is sugar sludge, right? The little treat at the end, the straight sugar and milk, right? And your mom tells you, don't put that much sugar on your cereal, but you do anyway when she's not looking, right? Y'all know what I'm talking about. That's for the corn flakes, the Rice Krispies. What are some other ones you put sugar on? What are those ones that taste so bad? Kicks. Kicks need some sugar. Don't you agree Kicks need some sugar? They're all right dry, but once you put milk on them, they're not very good. Okay. So saturated means no more can dissolve. Unsaturated means more can dissolve. Unsaturated, you can dissolve more. Now the third one is weird. It's supersaturated. Sounds like a superhero, like Dr. Strange, which I saw Saturday. Supersaturated. Okay, So what is supersaturated? This is how it works, and we're going to do a lab where you're going to see this. What you do is you heat it up. You add as much as can dissolve at that temperature, and then you cool it down really, really carefully. And when you do, the liquid does not get organized as long as you don't put a seed crystal in it or bump it. Have y'all seen those videos, or have you done this, where you get bottles of water and you get them right at freezing and then you hit it and it goes and it all crystallizes? Have y'all seen that? If not, it's on YouTube. I've done it before. We used to have a little refrigerator that would get bottles of water just to that height. If you hit it hard, it'll all crystallize. Now, that is not the same thing, because with the bottle of water, it's just water. But it's the same thing in that the liquid was not able to organize into the solid. You give it some energy and it organizes into the solid. So that's what that is. So we're going to do a little thing where I have some supersaturated solutions and you give it some energy and it crystallizes. So we're going to see that on Thursday. All right. So if something can dissolve, it's said to be soluble. I bet you've already know that word. And if something cannot dissolve, it is said to be insoluble. Insoluble. Did you already know those words? Okay, I'm going to scroll up. Wish me luck. Let's see if it'll do it. We first click on that. Now we're going to go over here and see if it'll do it. It's not doing it.
Oh.
I wonder what that's for. It's like you're hiding the answers. And da-da, and there they are. And now they're hidden, and da-da, and there it is. All right, we're going to have to start over. Boop. We're supposed to don't save. Try it again. Okay, we're right there. Okay, the next two words. So we did insoluble. I'm not going to write that one again. If things can mix, they're not called mixable, they're called miscible. It's almost the same word. And you know, this is multiple choice, so you all should be able to get it. It's called miscible if something can mix. And if something cannot mix, it's not immixable, it's immiscible. Had anybody ever heard of those words before today? Miscible and immiscible? You can mix it or not. Now, more about solubility. In general, we have a saying we like to say in chemistry, and it is that like dissolves like. That means that, remember when we learned in Unit 4 about polar and nonpolar chemicals? That polar chemicals dissolve polar chemicals. Like water can dissolve a water-based marker. And nonpolar is oil. It can dissolve nonpolar chemicals, like oil can dissolve Sharpie, or goof off can dissolve Sharpie. But water does not take off Sharpie, does it? No. And so it's that things that are not oil, they're like water, will dissolve in water. Things that are oil dissolve in oil. Now, there are rules for solubility of chemicals. That's what I was telling you. NAG-SAG is how I remember them. But you will learn those in college. You don't have to learn them for this class. Okay. Precipitate. We already learned this when we learned reactions in Unit 4. A precipitate is a solid forming in a liquid. And we learned about this when we learned the equilibrium rules, that you don't put it in if it's a solid. Yes?
Is this saying NASAG?
NAG-SAG. It's that nitrates, acetates in group 1 are dissolved, and sulfates, ammonium in group 17. So that's what it is. It's just a way to remember. It's like Roy G. Biv, but for the solubility rules. It's what's soluble. Okay. So, precipitate is a solid forming in a liquid, usually in chemistry. In the weather, it's in a gas, a liquid or a solid. Now, what is hard water? Hard water has dissolved ions in it, like calcium. and other soft water doesn't. It would have different things dissolved in it a lot of times because you can dissolve water softeners in there. And then hard water causes problems. I'm going to scroll. Y'all ready? Let's see if it'll let me do it.
Cat. That says cat, right?
Calcium ion Ca plus 2.
And what about the other one? That says Na.
That says nag, sag. It's the rules of the, it's like Roy G. Biv. It's something that helps you remember the rules for solubility. Okay? So I'm going to see if it'll scroll. Oh, it scrolled. Yay. So these are the problems with hard water. And we have pretty hard water here. Soaps and detergents don't lather well. We left off the R. Don't lather well. It makes soap scum. So we can get soap scum on our shower here. And it also makes minerals build up in pipes. So like when you go to Florida, they don't have hard water. They have soft water. So like it's hard to get the soap to rinse out your hair. A lot of times your hair is not good in Florida. And it tastes bad. It tastes really bad. That Florida water smells bad, yes.
The one underneath, don't.
Lather. Don't lather well, and it makes soap scum. Scum. Y'all know what soap scum is? It's what makes your shower door cloudy.
Oh.
That's soap scum. Also, it'll make it where there's like your sink might have sort of like a white powder on it. If you've ever had glasses get cloudy, usually that's calcium deposits, stuff like that. Now, there are some more things, some definitions you have to know with concentration. I'm going to try to scroll up. Excuse me.
Under that.
Build up.
Build up. It makes minerals build up.
Well, I don't.
Okay, so these are some more definitions. The reason why there are all these words is that figuring out concentration is different depending on what you're doing with it. When I make something, a chemical, I'm usually only making a little bit. I will often use this to mix up a chemical. It's called a volumetric flask, and that's how much I make usually. But if I was an industrial chemist, I would be making tons and tons of chemicals. So for me, it's convenient to use this little thing. If I was making tons of chemicals, these would no longer be convenient. I would need to weigh out the tons of chemicals and have a robot mix them. Do you see? So there are certain ways of doing this that I do where industrial chemists do it a different way. And that's why there's these different words, okay? So one way to figure out concentration is by mass percent. You take the mass of the solute, divide it by the solvent times 100. I don't do that as a high school chemistry teacher. The one I do has stars by it, because I do it. It got stars. I use something called molarity. And that's where I take the moles of solute, I figure out how many moles from the molar mass off the periodic table, and I divide it by a liquid amount, liters of solution. So that's why I use that thing there. The units for it are big M, it's moles, and the symbol is the square brackets. There's another one called molality. See how similar these are? It's what makes it hard. Molarity and molality. Molality, you do moles of solute over kilograms of solvent. So this one is the one where things are weighed out, and it's used in industry more, and its symbol is little m. Once again, what makes it hard is it's so similar. Molarity and molality sound a lot alike. Big M and little m are a lot alike. So you just have to learn this to match it on the test. So this is matching, okay? There's an old-fashioned thing. You don't see it that much. It's called normality. It's an old way of showing the concentration of acids. And they will take an acid that has just got one H, like hydrochloric, and its molarity is the same as its normality. But if it's something like sulfuric acid, H2SO4, that has two H's, you double it because what makes an acid acidy is how many H's it has. And the sulfuric has twice as many H's, so it has a twice as strong indicator. But I have been doing chemistry for many decades. I did in high school, I was a chemistry major in college, and then I've taught chemistry. I have ran into that very, very rarely. In fact, I had kind of forgotten about it. It had been so long since I had seen it until I was cleaning out the stockroom here, and there was an acid, a really old acid, that had its normality marking. I was like, oh, I don't remember this. What is this? And I had to go look it up. So now I put it in your notes because I'm like, well, they should learn it. So they won't be like me going, what is normality? I forgot that. Okay, also in common speech, we talk about how concentrated things are, and we'll say things are concentrated versus dilute. Dilute, you know that word, right? If something's not concentrated, if it's watered down, it's dilute or dilute. Okay, so we are going to have some math. You've got 1 page of math on there that you have to do. We have some graph reading and some math. And this is how you do the math. The math is going to be on Canvas, so you can check your answers. But your work for tomorrow is to do the 3 worksheets. I would advise you go ahead and do all 3 of them. Check your answers so that then all you have to do is study Wednesday and Thursday so you'll be ready to make a better grade. Some of y'all did awful on that last test. So some of y'all need to get on the ball a little bit better. Get this worksheet, your packet done so that you can study it. There are people who will sit there after the test doing their packet. How is that helping them for their test? It is not. So don't do that. Do your packet today, tonight for homework, and tomorrow. And the answers are on Canvas. There's really nothing to stop you from copying the answers down, and you would have it. But I'd rather you do the work and then check your answers. But do it. That's your work for tomorrow. Okay, so here is a problem, an example problem. What is the molarity? So what we're trying to get is big M, question mark big M. See, I'm annotating my work here. Of the solution that has 10 grams, so this is a mass of sodium hydroxide dissolved in 100 milliliters of water, that's the volume, in a volumetric flask. So on the test, there's a little question. I draw this. This is a volumetric flask. This is how I make up solutions. So what I do is so if I was doing this, I would look up the molar mass of sodium hydroxide on the periodic table. Then I would figure out what concentration I want and multiply the molar mass times that. And then I would put this on the scale and hit tare. Then I'd add the sodium hydroxide until it weighed the right thing. And then there's one little line on here. This is not like a graduated cylinder that has lots of lines. It only has one. I would fill it up with distilled water until the bottom of the curve, the bottom of the meniscus touches that line. I'd put a lid on it and shake it. Or I have these things that y'all have noticed. Have y'all noticed how some of the hot plates have 2 knobs on them? The second knob is there's a motor in there with a little iron bar. I put this little thing that looks like a Tylenol in there, and it's for the magnet. It's a magnet that will turn as the iron bar turns. And the hot plate heats it up and stirs it all at once. So it's just a great little thing. I love the stirring hot plates and the little magnet bars. In fact, while I'm thinking about it, I need to write down that I need to buy more magnet bars. Let me write that down. I only had one and I lost it. And then to get it out, there's this long magnet stick that you stick in there and you can pull the magnet out so you don't have to put your finger in the chemical, which, that's good. You don't want to ever put your finger in the chemicals. All right, so this is how the problem works. First, we're going to start with what you know. That's right. And I have 10 grams of sodium hydroxide in 100 milliliters of water. What goes catty corner always? What you already have, grams of sodium hydroxide. And where I get it is the molar mass. Here's my M&M. So I do the mass of sodium plus the mass of oxygen plus the mass of hydrogen, add them up. If you didn't learn how to do that for the last mini test, you need to learn how. So I'm going to write my 40 grams of sodium hydroxide here. What goes on the other side of the grams always? They're grams per mole, so what goes on the other side? Moles, 1 mole. I heard it. 1 mole. And if 1 mole goes here, what goes catty corner? Moles. Moles always goes catty corner. And what I want to do is I want it in big M, and big M is grams per liter. So this changed it to, is my grams, and then I need to change it to liters. So what I'm going to do is I'm going to say, make sure, hold on. Oh, I've already got grams. I'm good with that. I've got moles. I need moles here. But that is, I want to keep moles on top. I want milliliters to go away. So there are 1,000 milliliters, and I want this to be 1 liter. So now grams mark out and milliliters mark out, and I'm left with moles per liter, which is what I want. I don't want grams per liter. I'm not doing molality. I want moles per liter. Moles per liter. All right, so anything on top we multiply, anything on bottom we divide. And the answer is 2.5 liters. And I can put it in little square brackets because it's a concentration. Now, for the worksheet where you're going to be practicing this math, the worksheet sort of guides you through how to do it, and the worksheet explains it to you. So that might have been a little bit confusing. Don't worry about it. The worksheet makes more sense. Okay. The next thing are these things called solubility curves. They're graphs you have to be able to read on the test. I'm going to try to scroll up. Y'all ready? Do I need to wait? You got the problem? Okay. So let's go. I'm going to try to scroll without hitting the little thing. Very exciting. Okay, so how these little graphs work is, I love these kind of questions on the test because I don't have to study anything. I just have to understand how to read it. So on the test, I might say, how much potassium chloride dissolves at 50 degrees? So I would go 50 degrees up to potassium chloride and go over, and I see it's about 45 grams. Does that make sense to you? If I wanted to know how much potassium chloride dissolved at 80 degrees, I would look at 80 degrees, go up and hit the line, and then go over, and I see that it's 55. Or it might say, what temperature does it need to get 40 grams to dissolve? You go from 40 grams over to potassium chloride, go down, and it looks like it's 55 degrees. Now, one more thing about these charts that you have to be able to do. Saturated, supersaturated, unsaturated. Pay close attention. This is the test questions, how they work. I can tell you that I have a solution that has 50 grams of potassium chloride dissolved at 50 degrees. So I go up over 50 and up 50, and I see it makes a dot up here. It's above the line. So then the question is it supersaturated, saturated, or unsaturated? It's above the line, so it's supersaturated. If it was on the line, it'd be saturated, and if it's below the line, it's unsaturated. Does that make sense? That's all the questions that you will have on this graph. You're going to do a worksheet that will help do it. It's the last worksheet. It's the graph you're going to make using colored pencils. So on this worksheet over here, you're going to make a graph, and then you're going to answer questions on it. You draw the 4 lines in 4 different colors. When I grade this, I'm looking for 4 colors, and then you answer the questions. And if you can do this, you're ready for the test. The other side is just vocabulary matching to help you with the vocabulary. Okay, the next one is solubility of gases. We talked about solids dissolving. Now we're going to talk about gases dissolving. So now we're talking about Coca-Cola, soda pop. Who calls it pop? Who calls everything Coke? Who calls it soda? The soda people are starting to win. It used to be that everybody called everything Coke in the South. It was all Coke. Well, I have heard so many times, what kind of Coke do you want? Oh, I think I'll have Sprite. What kind of Coke do you want? Oh, I want Sprite. It's a southern thing. It's all Coke. But it sounds like soda is making inroads. But not pop, huh? Y'all don't call it pop? Pop?
My stepmom's from Michigan, she calls it pop, and we argue all the time.
Pop. So it's a Michigan pop. Ask her what kind of Coke she wants. Then she'll really not get it. Okay, so what does helps the gas? We already talked about this. Pressure and cold. And we know that cold doesn't exist, but you know what I mean. Your Coca-Cola will go flat once you open it, reducing the pressure. And if it's hot, it goes flat faster. So you've got that Coke out by the pool where it's really hot in August, and you take a little drink and then you go swim a little bit and you come back, it's flat. It's no good because it got hot and the bubbles came out. All right. So what is fizz? Fizz is carbon dioxide. And fizz is the same whether it's beer or soda or champagne. They add CO2 to it. Sometimes they add carbonic acid.
I thought you were going to say Carpaccio.
Carbonic acid is that, and they will cause the bubbles by adding the acid, and then the bubbles are released. So there's two ways to do it: by dissolving CO2 in it. Like if any of y'all tasted the what we made in the dry ice lab, you're not supposed to really taste things in lab, but this wouldn't hurt you. We put dry ice in nice little clean cups of water. If you tasted of the water, it tasted like seltzer because we had dissolved carbon dioxide in the water and made it a little bit fizzy. Anybody taste it in here? All right, I'm going to try scrolling it. Last little ideas. This is good. Y'all have done real good with this. I feel like you're understanding it. Okay. When ions are dissolved, they are charged. We learned that a long time ago about cations and anions. When you dissolve cations and anions, charged particles in solution, then they can conduct electricity. So if you put salt in water or sugar in water, it can conduct electricity. And that's why Gatorade has a lightning bolt on it. Okay, if you're exercising really, really hard and you're really, really hot and you guzzle down water really, really fast, what's going to happen? You throw up. You're going to barf. The reason why is you are salty. Your tears are salty. Your sweat is salty. You've noticed this, right? So in your body, remember when in biology you learned about osmosis and the cell membrane and hypertonic and hypotonic and isotonic solutions? Do you know what I'm talking about? Y'all remember that? So in your body wants there to be the same salinity, the same amount of salt on both sides of the cell membrane. So if you're all salty, everything's isotonic, it's got the good amount of salt on the inside and the outside of the cells, everything's the right saltiness, and you drink a bunch of cold, not salty water, then your body is already losing salt in your sweat. Your body goes, I cannot deal with this right now. I cannot saltify this water the way I need to make it salty. So we're just going to get rid of this water, and you throw up. And then you can die of heat exhaustion, dehydration, and stuff like that. So the University of Florida Gators, do we have any Gator fans here? This is your university. Developed for the football team Gatorade. That's why it's got Gator in it. And it is salty Kool-Aid. That's what it is. And you can chug it. You can drink it as fast as you want, and you will not throw up. So that's the point of it. You can drink it fast. You can replace the electrolytes. You can replace the salt. And you are getting salt depleted, working out so hard, you're going to have leg cramps and stuff like that. You drink Gatorade, and you're not. It's gonna be better. Now, what if you're such a Bulldog fan that you won't even drink Gatorade? What are other electrolytes like Gatorade?
Molarity.
Powerade. So for those of you who are such Bulldogs fan you can't drink Gatorade, there's Powerade made for you by the Coca-Cola Corporation right here in Atlanta. And also, what if you're sick and you've been barfing? What's the doctor going to tell you to drink? Pedialyte. Pedialyte is baby Gatorade. It's the Gatorade for babies. That's because they've been throwing up too much. They need to replace their electrolytes. You drink Pedialyte. Are the Pedialyte popsicles? Which are better, the drink or the popsicles?
You know there's like athletic Pedialyte, right?
Oh, so they got it for the grown-ups now. See, the Ped from Pedialyte was for like pediatrician. It meant child.
No, there's now
There's now grown-up Pedialyte.
there's now literal Pedialyte made for
Just give me
athletics.
7-Up.
Another example of an electrolyte is batteries. Batteries, like car batteries, also have is something that works by acids. So batteries are another example. Now, what are the effects of solute particles? We're on the last page. We can do it. We're almost done here. I should have known better than try to scroll that. I just was too tempted by that little button. Let's see if I can get it. Okay, has everybody written that down? Can I scroll?
Yeah.
Charged particles, electricity, batteries are another example. Can I scroll it now?
Wait, can you reverse Michael Jackson or something? So I can go black.
What?
Oh, no, just
All right, I'm going to close this out. Don't say. Go back in.
That's blackface. Okay, Ease.
Mad to Gatorade.
Jenny.
It is.
Okay, last little bit here. Y'all are doing good. Okay, now, this is if you add solute particles, it has an effect on phase change. So, if you add like salt to water, it causes a rise. It causes a rise in the boiling point. Boiling point symbol is BP. Now in science, we always like fancy words. It makes us sound smarter than we are. So we don't call it rise in boiling point. That's too normal. We call it elevation. That if you add salt to water, it causes the temperature that the water boils at to be higher. Why do we add salt to the roads if it's going to freeze? So the roads don't freeze up, right? So if you add salt, it causes lower freezing point. It also causes lower something called vapor pressure, which you'll learn more about in college. The symbol for freezing point is FP, and the symbol for vapor pressure is VP. We don't call it lower, that's not very sciencey sounding. We call it freezing point depression. It's not that this freezing point is sad. It means it's just lower. It's lower, so the ice doesn't freeze as the roads don't freeze up. Instead, they stay slushy because we put salt on them. And we used to never do that in the South. We did not buy salt. We only had icy roads like once every 2 years. We thought it was a waste of money. And then the Northerners would make fun of us when it would snow and we'd all just stay home and not go to work. Because up north, you don't get to just stay home from school and work if it snows. They have to still go. So they thought we were big babies. So then we got tired of being mocked, and now we salt our roads too sometimes. I think it's a shame. I liked our snow days. And it's bad for your car. That salt will make your car rust. So, all right. So if you add rock salt to your ice cream maker, listen, instead of the water freezing at 0, it freezes at -2. So it makes you get ice cream faster. Now, my ice cream maker was no good, so I gave it away to Goodwill. Shh, don't tell the shoppers at Goodwill. But it just never would freeze. It's like it couldn't handle the South and how hot it gets here. It'd just go around and around and around. You added ice, you added the rock salt, the ice cream salt, it didn't work. Okay, so colligative properties, that's a fancy science word you gotta know. And it is a chemical that depend on a property that the property changes depending on how many particles it has dissolved in the solution. So it's based on the number of particles. So that's just another vocabulary word for this unit. This unit is a lot of vocabulary and a little bit of math. Okay, so last thing is about soap. Polar molecules, you already learned in Unit 4, has charged ends like water. Non-polar does not have charged ends like oil. Soap and detergent have both. So how soap works is it's like a little fish hook. It's got one end that's non-polar, and that goes into the oil on your body. The other end is polar, and it gets connected to the water, and it pulls it off. So it doesn't work to just put water on you without soap. So I taught that for years. And then one time I had a girl wait until everybody left, and she said, Miss Blackburn, I never use soap. And she said, do I stink? You know, I just learned this in chemistry, and now I'm all upset because I never use soap. And I was like, why don't you use soap? And she had eczema, which is a skin rash, that the soap bothered her rash on her. So I was like, well, how do you take a bath? Do you just use, because no, you don't stink. How do you take a bath? And she said, I just use like oil. And she put conditioner and oil and stuff on her skin. Would that work?
Yes.
Yes. Because why? What did we learn in our notes? What's the rule? Like
Oil.
dissolves like. And unlike dissolves, like dissolves like. So she had sweat and dirt and stink on her. But then she put oil on it and then wiped the oil off, and it took it off. So you can actually clean without soap. Where our dirt is oily dirt and like dissolves like, what she would do is sort of like dry cleaning fluid. Dry cleaning fluid is a liquid, but it's like oil. Dry cleaning fluid uses a liquid like oil to clean your clothes, where normal cleaning stuff uses soap, the fish hooks. So she was like dry cleaning herself. And the other place, Caravaggio, listen, the other place where you see this is people will do this with their iron skillets. There are people who never put soap on their iron skillets. So to clean it, they'll put salt and oil and rub it on the pan and clean it that way. They don't get food poisoning. They don't get diarrhea. The like dissolves like. You actually can not use soap and get clean if you use oils to clean with. Have you ever used like oil to clean leather conditioner? It works, doesn't it? Because like dissolves like. All right, so we've got 10 minutes. For the 10 minutes, I want you to start working on your worksheets. I want you to stay in your seat. Don't go around the room. And if anybody wants to be assigned their exemption, now will be the time. Like, share, subscribe.